So any questions at all about the class or any of our content so far? We are about to finish doing stuff on irrotational and viscid flows and stuff. Hopefully you guys will enjoy the lecture today, which is kind of a different take on the concept that I suspect probably 95% of you haven't actually thought of before. Remind you that office hours are after class today. I'm gonna do what we do normally, just take like a quick 5-minute break and then just hop back on the call. Okay. Okay. Well, if there are no other questions and stuff, then let me remind you very quickly what we've been doing. We showed using the vorticity equation that irrotational flows are the same as inviscid flows. And of course, we care about inviscid flows because those are sort of half of the singular perturbation solution to the Navier-Stokes equation, right, in the large Reynolds number scenario. In the large Reynolds number scenario, we care about what happens in this case far away from a boundary or something like that, right? In those far away from a boundary, the vorticity equation shows that that inviscid flows when Reynolds number goes to infinity is basically the same as when there's zero vorticity in a fluid. And so the game became trying to figure out what solutions where we have zero vorticity in the fluid. And so we introduced this concept called the velocity potential. That automatically satisfied this idea that the vorticity is going to be zero because the velocity is going to be defined as a gradient of the scalar velocity potential, and then the curl of a gradient is always equal to zero. So therefore, the vorticity is equal to zero. And in order to make this a real fluids profile, to make this a real velocity profile, you have to make sure it satisfies continuity. And so then you end up having to solve this one PDE right here. Okay. So in an example for inviscid flow past cylinder, and then eventually got this on Monday. We figured out how to plot it and then also examine what happens at the boundaries and stuff. And this was that D'Alembert's paradox. We started to talk a little bit of, give you a little bit of a preview of what would happen when we. Am I not sharing my screen?
Yeah.
How are you guys? Why did you let me go that long without telling me this?
We
Okay,
thought you
sharing
were
screen now.
we thought you were explaining without the screen.
Yeah. I was
Yeah, I thought
for a second.
I was just going on like an extended monologue, huh? Okay. Yes, I was not sharing my screen. Hopefully you guys could at least picture what I was saying, but I'll try and go through it very quickly. You guys are all still there, hopefully, right? And can follow what I'm saying. Yeah. Okay. The internet connection is maybe a little slow on my side, and so I'm not sure what's going on, but this is reassuring. Okay. Quickly again, the second time, basically, velocity is the gradient of the velocity potential, and so therefore, from how we define the velocity potential, then therefore that velocity field always has a vorticity equal to zero because the curl of a gradient is equal to zero, right? To make it a real velocity profile, you have to make sure that it satisfies the continuity equation, and so the continuity equation then implies that the velocity potential has to satisfy this equation here with a Laplacian of it has to equal zero, right? We showed how we can use this, we can solve this equation given the scenario of inviscid flow past a cylinder. And then started to give you a little bit of preview of boundary layer theory and what happens at the surface of the boundary, drag forces and stuff like that. Okay. Parallel to that, what we also showed is that instead of artificially imposing that the vorticity has to equal zero automatically, we can also introduce this concept called a stream function, where the stream function now satisfies continuity automatically by this definition right here, right? And then if we want to actually find an inviscid irrotational flow, then we need to impose the condition that the curl of that of the velocity has to equal zero. And that actually gave us basically the same equation that del squared of psi now, the stream function has to equal zero. And then basically you can undergo the same almost identical math to figure out what the psi function would be and then figure out velocity potential.
I don't think we can hear anything right now if you're talking.
We can see you, but we can't hear you.
That's better.
How about now?
Yeah, we can hear you now.
Okay. I'm so sorry about all the technical issues today. I don't know what's going on. Okay, let me just quickly summarize what we've been talking about. Maybe this will be helpful. Okay, so I'll just call this summary of 2D irrotational flow. Okay. We talked a little bit about the velocity potential. That was called phi. Okay. By definition, this velocity potential is selected such that the gradient of this scalar velocity potential gives you the velocity, this velocity field that you care about, right? The reason why we select the velocity potential to give you this definition is because this definition automatically satisfies this condition by identity, that the curl of the velocity field is going to be equal to 0. This gives us an irrotational flow. Okay, and of course that's relevant because as we kept mentioning, inviscid flows are the same as irrotational flows. Okay, there is of course an additional requirement that this velocity potential has to satisfy. In order to actually be a real velocity profile. And that requirement is the continuity equation. Okay. And if you then carry this into the definition, what you find is that that translates into a PDE for the velocity potential that we have to solve given whatever situation we actually have. And in the example we did was flow past cylinder. I think in the example that you guys did for your homework, it was flow past a sphere, right? Sound familiar? In parallel with that, instead of, if you had chosen not to use the velocity potential, you could also have used something called a stream function. The math essentially looks identical, although the definitions are a little bit different. Because for the stream function, the definition is this. Is that, right? And the reason we select that definition is because the stream function, as defined this way, automatically satisfies the continuity equation. And if we want an irrotational flow, then we need to impose this additional requirement. My OneNote just glitched, okay. Screen sharing just stopped. We're back. Hopefully you can see my screen. Yes. Okay. I don't know what's going on today, guys. I really apologize.
No worries.
It automatically satisfies the continuity equation from the stream function does. But then in order to make this an irrotational flow, we need to impose this additional requirement that the curl has to be equal to 0. And if we do that, then that again implies a new partial differential equation that we have to solve, which turns out to be the same differential equation that we had before for the potential function, okay? All right. A few notes before we move on, because both the stream function and the velocity potential are actually useful ways of solving a problem. Again, you can take your pick. Either one is perfectly fine for looking at 2D irrotational flows, okay? But just a few different notes. Like I said, all these are for 2D irrotational flows, But it turns out that the velocity potential applies for 3D flows too. Okay, so I'll say also applies to 3D. Okay, and that's just because, you know, this gradient here is a 3D operation, right? If you can take a gradient of a scalar field in 3 dimensions or something, or as many dimensions as you want, actually, right? And you know that final velocity profile is still going to be irrotational, and then so you could use this for 3D irrotational flows as well. Okay. The stream function also has a few different notes. Of course, the stream function only has definitions in 2D. Those definitions are different in other coordinate systems. And other coordinate systems are a little bit more complicated too, because like if you imagine what a 2D flow looks like in cylindrical coordinates, what that really means is that there's either a VR and a V theta, or there's only a VR and a VZ, or there's only a V theta or a VZ. And those definitions of the stream function actually depend on which ones you're actually picking, right? In Cartesian coordinates, it's not as complicated because you can always just redefine whatever your axes to be X and Y, right? But in cylindrical coordinates, it actually makes a difference whether you're talking about VR or V theta or VZ, or in spherical coordinates, of course, V phi, V theta, or VR, right? So just to give you an example, if we have a 2D flow in cylindrical coordinates that looks like this, that has a VR and a V theta component, then the definition of the stream function looks like this. And then of course there's no VZ component, right? And so I'll say these are different. If you have in like RZ cylindrical, you could also have like R theta spherical. In other words, you only have velocity in the r and theta direction in the spherical coordinates, right? Imagine like you had something moving like revolving around a sphere or something like that, right? And you can look up all these definitions. These are all well known. You can find them in Dean 6.8, for instance. This is table 6.8. Okay. The last note I'll mention also has to deal with the stream function. I'll say the stream function is also is useful not just for irrotational flows. Right. So we're going to return to this a little bit later on in the future. Like when we start talking about boundary layer theory and stuff, it actually turns out that the stream function will be useful in those definitions. The reason why is just because the definition of the stream function, unlike the velocity potential, where the velocity potential, the definition basically imposes that you have to get an irrotational velocity field. The definition of the stream function just says that your velocity field has to satisfy the continuity equation, and all velocity fields have to satisfy the continuity equation, right? And so this particular like Laplacian of stream function has to equal 0 only comes about specifically because we care about irrotational fields, right? But if we don't care about that, then we're just going to get a different differential equation for the stream function that we could solve as well, right? And so this stream function becomes useful in other contexts as well. Okay.
Jill, I have a quick question.
Yeah.
So earlier in the course we were talking about the streamlines, and we talked about the like P, the stream function, or I don't know if that was called the stream function, but how does that like the function P we had talked about there relate to this stream function?
I don't remember what the P was.
I'll go back and check my notes.
P was the trajectory parameter.
Yeah, I think the P might have been like that was like sort of path lines versus streamlines, if I recall correctly, right? And the streamlines were we found using a different method, and I can't remember what that method actually was off the top of my head anymore. But it's a parallel method that sort of works just as well as what we're dealing with here. This might this might actually be even easier because all you have to do is just set psi to be some constant, and depending on what constant you pick, then you get your streamlines.
That makes sense.
Later on today, actually, I'll show you several examples of where this could potentially be useful. But before I do that, I'm going to need to introduce a new sort of concept here. Okay, and you're going to wonder for a while, because it's going to take me a while to link this back to fluids. You're going to wonder for a while why this is interesting. But I'm going to talk to you today about complex analysis. Okay. How many of you guys have taken a complex analysis class before? Or tried to like think about calculus of complex numbers and stuff? Good. Like I said, 95% of you guys have maybe never thought about things like this before. Okay. For the half of you that don't have your videos on, I'm going to assume that the answer is no. Okay, but it would be nice to see your face. All right. I promise you guys that this will be relevant to fluid mechanics, but it'll just take me a second to actually get there. But talking in general about complex analysis, okay? We've talked a little bit about complex numbers so far in the class when we talked about Stokes' second problem and Fourier transforms and stuff, but this is maybe an even more rigorous and complete way of thinking about it. Okay, in complex analysis, we typically think of a complex number as written, the letter Z is typically used. It's just written as x plus iy, basically x being the real component and y being the complex component, or the imaginary component, okay? So let this be a complex number. Okay. That means that, as I mentioned, x is the real component of z. That's usually denoted like that. And y is denoted as the imaginary component. Okay. And of course, x and y are real numbers. Okay. And that's how we think about complex numbers, basically. Complex numbers, another way of thinking about it is it's an ordered pair of two numbers. It has an x and a y. You know, any sort of complex number, you know, all numbers that we deal with are actually complex numbers. They just have an imaginary component of equal to 0, right? But you could also think about it as an ordered pair of two numbers together, right? We also think about ordered pairs all the time. Those are just coordinates on a set of axes, right? And so just like how you can think about axes as Cartesian, you can also think about complex numbers as cylindrical, right? So say complex numbers can also be represented as r times e to the I theta. Okay, and this is for real r and theta. So r and theta have to be real numbers. Okay, the reason why we would express it like this is because we've talked a little bit about this earlier in the class. E to the I theta can be written like this. That's an identity. Okay, and so what that implies then is, given this definition, z equals r times e to the I theta, then z can be written r times cosine theta plus I times sine plus I times r sine theta. Okay, and this is kind of convenient because you can immediately see that this sort of gives us a polar representation, how to represent complex numbers in polar coordinates, right? You can see then that therefore x, comparing this definition right here to this definition up here, x could be written like that, and y can be written like that. And of course, those are polar representations, right? It's a polar representation. Of z. Okay. If you like things drawn out, which I personally do, normally, you know, when you were first learning about math in like 3rd grade or something like that, or however long, they probably introduced you to a number line, right? And so all your numbers would fall along this line. 0 would be in the middle, and then you'd go off to positive infinity here and negative infinity over here, right? With complex numbers, because you have both a real and an imaginary component, then you talk about a complex plane. And so if you have just some random number, a random complex number that we'll call z, then the real component of that is x right here, and the imaginary component is y right here. But given the way that we just introduced with this complex, with this polar representation, then you can think about an r here and a theta here, right? There are a few other operations that we care about. For instance, the magnitude of a complex number. You typically write that as that. It's basically the same thing as an absolute value. Okay. That can be in polar coordinates. That can just be r, right? As is obvious from this. That's just the distance from the origin. Okay. In Cartesian coordinates, then the way that you actually write this is x squared plus y squared, right? Square root of x plus y, x squared plus y squared. There's another operation that we care about sometimes with complex numbers that's called the complex conjugate. Okay. That's typically denoted as a bar over the z. That's written as x minus iy. So if you have a z right here, then the complex conjugate of z is down here. Okay. And so another way of writing the magnitude in general, regardless of what coordinate system you're in, is z times z bar here. Okay. Because if you were to actually multiply out x plus iy times x minus iy, you would get x squared plus y squared like this. You can also take the angle of a complex number. You can also sometimes call it the argument, that theta, or I'll say, all right, it's typically denoted as arg of z. And that's just, in polar coordinates, that's just the theta. Okay. In Cartesian coordinates, that's written as inverse tangent of x over y. That's for x greater than 0. And of course, when x is less than 0, then you have to add a pi to it. Okay. Hopefully this is not new. Like, have you guys mostly seen sort of this before? Or if you haven't seen it, this is hopefully mostly intuitive to what you guys thought about for complex numbers stuff. Yes. I'll mention this polar representation is kind of useful in certain cases. Representation. Is useful for certain functions. For example, at some point in the past, I think when we were talking about Fourier transforms, I asked you guys if anyone knew what the square root of I was, right? If you knew about the polar representation of complex numbers, you could actually figure that out really easily. Okay. If you guys remember what that was, it was something like 1 plus I divided by the square root of 2. Does it sound familiar at all? And then I even spent some time like actually multiplying those two out and then multiplying 1 plus I times divided by square root of 2 multiplied by 1 plus I divided by square root of 2. And then showed you that that gives you I, right? Well, if you knew about the polar representation of complex numbers, then that's actually pretty easy to calculate. The square root of I is obviously I to the power of 1/2, right? The polar representation of I is, well, if you have I right here, so in other words, we have 0, 1, then the R, the magnitude is going to be 1, and the angle is going to be pi over 2, right, basically on the y-axis. Right? If you don't believe me, you can take r1 times cosine of pi over 2, and you'll get 0. And r is 1 times sine of pi over 2, and you'll get 1, and so you get I, right? But this representation allows us to do pretty easy power here. E to the I times pi over 4, right? And e to the I times pi over 4 is just, well, r times cosine theta, but theta being pi over 4 now, the cosine of pi over 4 is what? Square root of 2 over 2, right? And the sine of pi over 4 is also square root of 2 over 2. In other words, 1 over the square root of 2. And so this gives us 1 plus I over the square root of 2. Okay. And again, if you actually multiply out 1 plus I divided by square root of 2 times itself, you will get I. Okay. Cool. Have any of you guys seen that for actually calculating square root of I before? You can also do weird things like this where if you want to take like the log of I, you can do the same thing here, right? And you'll get something, you'll also get some actual number here that you can think about. Now this is all complex number stuff, and so like whether this is actually useful or not to know what like the square root of I is or the log of I or something like that is unknown at this point. But hopefully I'll be able to show you guys how this is important in fluids. Before I can do that though, I need to think about complex functions because we're going to talk about calculus. Okay, complex functions. Just like how a normal function, a real function, is something that takes an input and gives you an output. In real analysis, it's, you take a real number and it outputs another real number. A complex function, which we can call f of z, it takes a complex number and gives you another complex number, right? So one way that you can write this, or is very commonly written, is that. Okay. This basically converts a complex number x plus iy, which, a lot of times we like to call z, right, into another complex number. And that complex number is u plus iv. Okay. Hopefully not rocket science here, right? All we're doing is just taking a function and using a function to take a complex number and convert it into another complex number. Okay, if we have a complex function, we could actually take a derivative of a complex function, right? Now you guys know what a derivative is in real life or in real analysis, right? That's, for instance, the slope of a line or something like that, right? In complex analysis, that derivative is actually something pretty similar, but it's a little different now because you actually are converting two numbers into two numbers, right? But I'll just write down for now, what is a complex derivative? For instance, if you have a complex function that looks like this, it's a perfectly upstanding function right there, right? And you can take a derivative of that. Can anyone guess what the derivative of that complex function is? Any guesses at all?
You just do it component-wise, like the derivative of u with respect to z plus
Something
derivative
like that.
of v with
Something like
respect to.
But I'll just posit that it's actually something even simpler. It's actually just 2z. Okay, it wasn't a trick question. Okay. In fact, most of the rules that you know from real analysis actually applies directly to complex analysis. Okay, power law still applies. Derivative of sine is still cosine. Derivative of log is still 1 over z. All that stuff still perfectly applies to complex numbers. Okay, but Adrian, you got into something. That's really important, because basically, f is actually two functions that depend on two variables. Okay, just like how complex numbers aren't really complex numbers, it's actually just two numbers that we decided to smush together and have an I in there somewhere. Okay. And there are certain rules that you have to follow, like complex conjugates, and you know, every time you multiply an I and an I multiplied together gives you a real number again, or something like that, right? A function, a complex function f of z is actually two functions, right? Those two functions are u, which depend on x and y, and v, which also depend on x and y. And so, just like before, where the derivative of a function can be written in terms of this limiting finite difference, we can do the same thing in complex numbers. Okay? But of course, when I say that delta z goes to 0, what that actually means is that delta x plus I delta y go to 0. So in other words, both delta x and delta y go to 0, right? So what I mean to say is that this above definition here must be true regardless if we let delta x go to 0 first, or if we let delta y go to 0. Okay? Let's see what happens if we do this by individual components in the way that AJ was talking about. So one way of evaluating this f of z, or this complex derivative f prime of z, is we can let delta x go to 0. Okay, and we can say already, let's have delta y already be 0. Okay, then my derivative becomes this. Right, minus f of x plus iy divided by delta x. Okay. Likewise, I could also define my complex derivative as the limit as delta y goes to 0. Right? Then the way that I should write that is f of x plus iy plus I delta y minus f of x plus iy. And then my bottom case, in the bottom here, it's my delta z, but of course my delta z is equal to delta x plus I delta y. And so my bottom here is I delta y. Okay? Let me go ahead and simplify this a little bit, but I just want to remind you that what we actually have here is a function of two variables, right? Of the real component and the imaginary component. And so an equally valid way of writing this first derivative here, this first quotient here, is that. Right? Remember, it's a complex function is basically two functions as a function of two variables, right? And those two variables are the real component and the imaginary component. In this case, the real component is x plus delta x, and the imaginary component is y. So that's why I get x plus delta x and y, right? But of course, you guys maybe recognize what this derivative is, right? This is partial f partial x, right? Remember, f is a function of both x and y, and I'm basically doing my derivative in x here. And so I get df dx. Or another way of writing this is, remember, my f is actually two functions, right? So I could write this as du dx plus I times dv dx, because f is just u plus iv, right? Okay. This other way of doing things will look pretty similar, right? I'm going to pull my 1 over I out front over here. So I'm going to get a 1 over I here. But then everything else basically looks the same. I have a limit as delta y goes to 0. F of the real component here is x, and the imaginary component is y plus delta y minus f of xy divided by delta y, right? And then just like before, the value of this limit right here is the partial of f with respect to y. One over I is just negative I, right? You can multiply the top and bottom by I and you'll convince yourself that that's true. Okay, so 1 over I here is just negative I. And of course, df dy is just du dy plus I dv dy, right? So I get negative I times du dy plus dv dy, because I had an I times dv dy, but if I multiply that by negative I, then I just get 1. So I have dv dy here. Okay. So those are two equally valid ways of taking the derivative of f with respect to z. And I'm actually getting two different answers here, right? And so what that means is that if this derivative df dz exists, then the following equations must be true. We have to have that du dx has to be the same thing as dv dy. In other words, this real component here has to be the same as this real component here, right? Otherwise, the derivative would be different depending on which way I take the derivative. Okay, and that can't make sense. And then likewise, du dy has to equal negative dv dx, right? The imaginary components also have to be the same right here. Okay. This is a condition that is true in complex analysis that's not necessarily true in real analysis. In real calculus, when you take a derivative, you just take a derivative. Okay, but because complex numbers are strange in that it's actually two functions in terms of two variables, and there's a sort of I thing that allows you to potentially convert between the two functions and variables and stuff. In order for a function to be differentiable in complex analysis, it has to first satisfy these conditions. Okay. There's a name for this condition. These are called the Cauchy-Riemann equations. And like I said, most real functions that you've dealt with so far have been differentiable. You just take the derivative. You don't even really need to think about it, okay? But complex functions are special in that it has to satisfy these equations in order to, and so like if you just write down any random complex function, it doesn't necessarily have to satisfy these equations. And if it doesn't satisfy these equations, then you can't take a derivative of it. Okay. There's a special name. This is so common in complex analysis that there's a special name for differentiable functions. So complex differentiable functions. They're called analytic functions. Okay. And as I mentioned, if you just write down some random complex function, it's not necessarily going to be differentiable. In fact, it turns out for most of the stuff that you could think of, they're typically analytic. Okay. So most functions that you could think of are analytic. Let me just give you some examples of analytic functions. Polynomials are all analytic. That's why when I talked about f of z squared here, we can immediately say that the derivative is 2z. And the rules of derivatives actually still apply. Okay, so like you can use the power rule, for instance. So polynomials, in other words, powers, right? Logs also work. Logs are analytic as well. Exponentials. Okay, e to the x, or sorry, e to the z, for instance, and the derivative of e to the z is still e to the z in complex analysis. It's still the same thing. Okay, trig functions, sines and cosines and stuff like that. And just, I'll say etc here because there's just a lot of complex analytic functions. And like I said, most of the nice functions that you could write down actually turn out to be analytic. It's only when you start to get into weird things where like you take a function of only the x component or only the y component, then you start to deal with those situations. Okay. That's all I'm going to say about the rules of complex analysis. Okay. But I promised at the beginning of this little unit that I'm going to relate it to fluids again. And so I'm going to do that right now. Okay, so here we talked all about complex functions. Let's relate it back to fluids. Okay. You guys remember when what I summarized at the very beginning of lecture, right? We talked about the potential function and the stream function for 2D irrotational flows. Right, let me remind you guys about that in just a second. And the potential and the stream functions. Okay. The definition of the potential function was that Vx is defined as the scalar gradient, or the gradient of the scalar function phi, right? And so Vx is given by that. And of course, Vy is given by d phi dy, right? Sounds familiar? If not, just scroll up in your notes and you'll see it immediately. That was in that little summary that I wrote, right? The definition of the stream function is written like this. Vx is defined as d psi dy, and Vy is defined as negative d psi dx. Okay? Check it out. You guys can see me waving my mouse around, right? Do you guys see the similarity here? It turns out that the potential and the stream functions satisfy the Cauchy-Riemann equations. Okay. What does that mean? Well, u and v right here are just the real and the imaginary components of some complex function, right? And if u and v, or in this case, psi and phi, satisfy the Cauchy-Riemann equations, what that means is that the master function that contained u and v needs to be an analytic function, right? And so what that means is that once I have an analytic function, I can take the real component And that's a potential function. And I can take the imaginary component, the v component, and that's a stream function. Okay, and so what that means is any analytic function I can write it like this. Will describe some 2D irrotational flow. And I'll put 2 exclamation points there because I think it's really cool. Right? Do you guys think that's kind of cool too? I don't know. It just means that you can write down any function you want, z squared, for instance, and we'll talk about that in a second, okay? You can just literally write down any function that you want. And then you just take the real component, and it's vx, and it's the potential function. And you take the imaginary component, and it's the stream function. And then you apply the rules for potential or stream functions. You can figure out what the velocity field is, what the velocity field actually is, right? And then you do all the things that you would normally do, like you can do Bernoulli's equation to get pressure, you can get flow rates, you can get all sorts of fun stuff. You get the stream function, you get streamlines and stuff like that, right? For instance, like if you just give me some random function, we're going to look at several examples in just a second, right? But if you just give me some random function, then the derivative of that function, df dz, right? As we mentioned up here, df dz right here could be written as partial f dx, right? And so one way of writing that is d phi dx, right? Plus I d psi dx. And by these definitions up here, d phi dx is just vx. And d psi dx is just negative vy. Right? And so if you want if you just write down any function you want, all I have to do is just take a derivative. And then the real component of that derivative is going to be equal to my vx. And the imaginary component is going to be equal to negative vy. Right? And if I even want like the magnitude or the speed of the velocity field at any given position, then that's just the magnitude of my derivative, because that's the magnitude of this is just going to be vx squared plus vy squared, right? I thought that was kind of cool. I don't know. And of course, you care about the magnitude because that goes into Bernoulli's equation, right? Okay. Cool. I just wanted to soak that in for a second, but apparently no one cares besides me. Here we go. Examples. All right. Like I said, you can just write down any function you want, and you can basically figure out what the flow profile for that corresponds to. Okay. And there's even some other tricks that makes this even more fun. Okay, let's just say we have a general function that's just some constant times z. Okay, it's a pretty simple function. You could write it like this in terms of an imaginary and a real component. Okay, as we set up here, the real component is the potential function. Okay, and the imaginary component is the stream function. Okay, you can also figure out what the velocity components actually are, what vx and vy are, right? Because you know what the derivative of some function a times z is, right? That derivative is just a. Okay, and so the real component of that is a, right? And the imaginary component of that is 0. So this particular velocity field is just vx equals some uniform number, right? What we have here is a uniform flow in the x direction, okay, with a velocity of a. You could also calculate like the speed of this flow, for instance, the magnitude of our complex function here is just the speed of our flow, and that's obviously just going to be a, right? Now, if we didn't know that, you could also look at the stream and the potential functions and figure out what the flow should actually look like, right? The stream function set to be equal to some sort of constant, to some various constants, gives us the streamlines, right? And so the streamlines here would be a times y equals some constant, and that constant can vary. And so the streamlines here is y equals some constant, right? And so the streamlines will look like this. Right? Give myself some axes here. And if A is positive, for instance, then the fluid just goes that way. Let me also write you could also put in lines of constant psi or constant phi as well. The lines of constant psi, the stream function, gives us the streamlines, right? But the lines of constant phi are lines of constant velocity potential. In this case, we get ax is equal to some constant, so x is equal to some constant. So those are vertical lines, right? These are lines of, so these are streamlines here. And you get that by setting psi to be equal to some constant. These lines right here are lines of constant potential. The lines of constant potential are something more along the lines of it's the velocity is always going to be perpendicular to those lines, right? The velocity potential is like it's like if you were to take the gradient of a gravitational potential, then the force is always going to be perpendicular to those lines of constant potential. It's like the velocity is trying to move downhill from those potentials, if you will. Okay. One thing to note, for instance, is that I'll just write note here. The psi and phi contours they're always perpendicular. Okay. Maybe I can do one more. I think I've got just a few minutes left. Maybe I can just do one more. Does that sound okay with you guys? Okay, example 2. I promised you that we would do f squared or z squared. So let me do that. I'll actually put in a constant here, alpha over 2 times z squared. Okay, we can find the real and imaginary components of this. The way that you would have to do this is you have to note that z is equal to x plus iy and actually multiply it out. Okay, and so when you actually multiply that out, you have an x times x, and you have an iy times an iy, which gives you a negative y squared. So you have an alpha over 2 times x squared minus y squared. And then you have a I alpha xy, because you have the cross terms, x times iy, and then iy times x times alpha over 2. Okay. That gives us a potential function that looks like this. And a stream function that looks like this. Because again, the potential function is the real component and the stream function is the imaginary component. Okay. If you wanted to, you could also calculate the actual velocity components here, vx and vy. To do that, you take a derivative of the function. You don't have to do that. Once you're given the potential and the stream function, you can also just apply those definitions up there from earlier above, right? But I don't necessarily need to do that here. I can just use this. Okay, it's just one step, maybe easier. The derivative of f with respect to z is alpha times z. Okay. And so that's alpha x plus I alpha y. I don't know why I said x here. And so what that means then is that Vx is equal to alpha times x, and Vy is equal to negative alpha times y. So what does this plot actually look like? What does this flow field actually look like? Maybe it's easiest if we actually just plot the streamlines. What we have is alpha xy is equal to some constant, right? And so if we solve this for y, for instance, we get y equals some constant over x. Y equals 1 over x, or y equals 2 over x, or something like that. Does anyone know what those look like? Those are hyperbolas, right? Okay. And if alpha happens to be positive, then you get something that looks like this. Right? These are the streamlines. You can maybe believe me as well a little bit, because if you stare at Vx and Vy, you can maybe convince yourself that like if alpha is positive, then over here you should have velocity moving in the plus x direction. Over here you should have velocity moving in the negative x direction, right? And then the farther you are from the x-axis, the larger the y component becomes, and so the more vertical it becomes, right? You can also look at the lines of constant phi here. Those are the constant potential lines. That's also a hyperbola, but that looks like this. Okay. Right. You could also calculate like the speed of this flow. You just take the absolute value of this, the magnitude of this. One note that I'll mention. We can always replace streamlines with walls. Okay. And so these notes are actually halfway important. I'm going to box all these notes. In normal fluid flow conditions, you can't always do that. But we're talking about inviscid flow, and so there's no slip near a boundary, or the no slip condition near a boundary doesn't necessarily apply here, right? And so what I mean when I say that is, if we wanted to figure out what the flow profile looks like when, let's say, a fluid goes into a wall, we've essentially done that already. This flow profile that we just solved for is just the top half, or this piece right here is just the top half of this flow profile right here, right? So I'll say this is the same. So that gives us sort of a nifty way of calculating flow profiles and stuff. Given what if we're already given like a function. Okay. All right. On Friday, I'll start with just several more examples of this. But it's really cool. I think like you can just sort of write down any function that you want, and you basically just get a flow profile for free. Okay. All right. I'm gonna take a quick break. I'll be back. Let's say 4:05, and then if anyone wants to stick around for office hours, I'll see you guys then. All right. See you guys later.